Hello everyone. Today's lecture is on separation of natural gas. So, this is our production system from where we are producing the natural gas, and when natural gas is reaching to surface, the first equipment it is encountering is separator. That we understand, we repeated this several times. Now, today's lecture will be dedicated to understand how separator do job, how to select appropriate separator, and the other accessories those are related to separator will be discussed. In this lecture, we will also understand how to choose appropriate separator. So, the separator shown here is for separating three phase water, gas and oil. As we know, the fluid produced from reservoir, even it is a gas reservoir, oil reservoir, it produces almost all three phases along with some solid particles. In that case, what happens? Some of the cases you will see another device before the separator, that is called scrubber, that is just separate out solid particles and the fluid is entering into separator, and the separator is designed based on the composition of the fluid being produced. For example, if it is just a two phase oil and gas separator, or it is three phase separator oil, gas and water, the separator should be vertical, horizontal or other type will be discussed later on. Important point is, when the fluid is reaching to separator, it is getting separated, the separator job is very critical, because the separator will decide how the other units are going to work. As shown here, on the downstream side, after the separator, when the fluid is going to be treated for recovering the water, that is free water or the moisture present in the natural gas, or recovering the valuable hydrocarbons, means higher carbon number hydrocarbons, those are more valuable, we can separate them out and we can sell them separately, and undesirable compounds, for example, H2S, CO2 and other compounds, those need to be separated. And the job of other units, how effectively they are going to work, primarily depends on separator. Thus, choosing appropriate separator and designing appropriate separator is very most important. We will see separator at other places also, other than immediately after the production is happening. The separators are also required at other units, for example, dehydration, sweetening, recovery of hydrocarbons. Even before the compressor, we need separators where we can separate the phases. So, the separator job is separating the phases, primarily separating gas from the liquid in the case of natural gas production system. At other places, the separator is appearing, it is also named as knockout drum, scrubber or mist eliminator. Why we need to do all these steps? Because there is some condition from the pipeline design or transporting natural gas through the pipeline that has certain condition, and separator and other unit should meet those guidelines before the natural gas can be transferred through the pipeline. For example, BTU content, mostly it is methane gas that goes to pipeline, but depend on the BTU requirement, significant percent or even small percent of higher hydrocarbon compounds are also present, because we know when higher hydrocarbon compounds are present, the energy content of the natural gas goes up. So, depend on the pipeline design, what is the requirement at the other end, the composition of the natural gas should also be maintained. Dew point temperature should be maintained. So, the phase separation is not happening within the pipeline. Foreign compounds like H2S, CO2, they are not present, solid particles are not present when the natural gas is transporting through a long distance pipelines, no particulate matters present, sufficiently dehydrated. So, if water is there, acid gases are there, corrosion may happens, it may damage the pipeline. So, the beginning happens from the separator itself to meet the pipeline's requirement. Meeting all the pipeline requirements start from the separator, and the separator separated phases based on several principles. Those separator can be gravitational wave separator, centrifugal separator, cyclone separator, mist separator. There are various names of the separator. They work and separate the phases. The optimum pressure and temperature at the separator is very important. For example, the fluid is reaching to separator. How it is going to separate gas and liquid depends on the composition of the stream that is reaching to separator, and the separator is being operated at particular temperature and pressure. From our phase diagram class, we understand even the gas composition, those are in the gaseous phase under the reservoir, when they are being produced, they are reaching to separator, significant pressure drop happens. So, from the phase diagram we say A is the point, reservoir temperature and pressure condition, where we are having only the gases. If it is isothermally coming like this, we are okay, we are having only gaseous compounds at the reservoir condition as well as separator condition. But if temperature is changing, pressure is changing, and when we are reaching or entering in the envelope of two phase region or multi-phase mixture system, we are going to get some of the condensate or liquid compounds, those are releasing out from the gaseous substance. Thus, the separator decide exactly under what condition it should be operated. So, we are having recovery of the higher hydrocarbon compound there itself. When natural gas is being produced, it may contain oil, water, solid particles along with the gaseous composition. Before the separator, a kind of a scrubber or heater combination can be used, because after the choke pressure drop will happens, hydrate may get formed, that is why it can be heated. We cannot heat entire separator if the pressure drop is happening directly at the separator. Before that, we are having kind of a device, we called it scrubber, where the solid particle are getting removed, as well as whatever the temperature drop is happening because of sudden pressure change or because of Joule-Thomson effect, it is being, the section is being heated to maintain the temperature. So, when the gas is reaching separator, again pressure drop will happens, and under that condition the separation of gas and liquid, those are actual present in gas and liquid condition, as well as some of the compound of the gas, those may go to liquid, or some of the compound of the liquid because of revaporization is going to gas phase will happen at the separator. We understand when our reservoir is kind of a condensate reservoir, we are in the region of critical point and Crichton-Therm temperature and pressure of reservoir. Under this condition, what we are going to get? The fluid, when it is reaching to separator at a particular temperature and pressure, the phase separation will depend at what pressure the separator is being operated. The operator has the flexibility to operate the separator using the back pressure regulator. He can maintain the pressure at the separator, but at what condition that should be maintained is the point to be decided, because significant amount of the hydrocarbon liquid can be recovered at separator itself, but again depend on the BTU need in the pipelines, at what conditions we should operate it should be decided. Another point, if the fluid composition are changing, we understand when the fluid composition are changing, the phase envelope diagram will also get changed, and when temperature and pressure condition are changing, from this phase diagram we understand the composition of the phases in the liquid phase and the gas phase, or the amount that is going to be the in the liquid phase and in the gas phase will also get changed. That is why it becomes very important to understand how to choose separator and how to decide the operating condition of the separator. Optimum pressure and temperature, if we are operating under optimum condition, the temperature and pressure condition are set in such a way, we are getting the maximum liquid recovery, that is also called the NGL, natural gas liquid compound, we are able to separate, we are generating the revenue. We can sell out those liquid compound to earn money, or those are having separate market at a higher value, but it is not easy to operate that under optimum condition. Sometimes the storage facilities or the other surface facilities available should also be adequate enough to storage those compound. They are not going through again revaporization and losing the valuable hydrocarbon compound in the form of vapor out of this production and processing system. Thus, it becomes important to know what are the composition of natural gas that is being produced. We understand the natural gas composition mostly dominated by methane. If it is a dry gas reservoir, then we are having several hydrocarbon gases, some non-hydrocarbon gases as well as liquid like H2O may be in the liquid or may be in the vapor phase, and some traces amount of the very valuable rare gases. We are going to deal with the system with the help of a separator to separate them out, separating into different phases. So, if we see separator works on the gravity separation or in a centrifugal segregation. There are some other ways also, but mostly it is designed based on the gravity or centrifugal forces. Separator function, as mentioned already, separating the phases is the job of separator, but when we are choosing particular separator, it should have 4 primary function within it. First one, when the fluid is entering, primary phase separation is happening, means the liquid hydrocarbons, those are already in the liquid phase or those are heavier hydrocarbon compounds, are getting separated from the gas at the inlet condition itself, in the primary separation itself. Further, when the further refining is happening, the separator is able to remove entrant liquid mist from the gas. That should be whatever the liquid compound, those are entrant in the gas phase, should also be removed. That should be the job of the separator. Further, in the next step, the entrant gas within liquid, or the liquid is also carrying some amount of the gas, either in the solubility form or in the condition of just free gas that is associated with the liquid. The separator design as well as operating condition should be in such a manner the entrant gas is also getting recovered from the liquid. The last one, it is not only separating the phases, we are able to separate the gas from the liquid or liquid from the gas within the separator, but there should be sufficient room or design criteria should be chosen in such a manner the liquid and gas phase are not going to re-enter again, they are getting separated in the separator and they are also leaving the separator separately, means gas is going from one place, liquid is going from other place. There is no chance where they are going through re-entrainment process. Considering the function of separator, separating the phases, considering these 4 primary parts, the separator component could be divided in 3 parts. First one, the inlet. At the inlet itself, primary separation should happens. The liquid and gas should get primarily, means the heavier hydrocarbon or the liquid phase hydrocarbon compound are all getting separated at inlet itself because of the gravity. Large settling section, this also known as disengagement section. So, the separator, either it is a horizontal, vertical or spherical or any other type of the separator, it is having sufficient area or room where the disengagement between the gas and liquid phase is happening. It means we are allowing liquid droplet to settle out the gas stream. When the gas is travelling up carrying some of the liquid compounds are getting separated because of the gravity. There should be sufficient length, in case of the horizontal sufficient length, in case of vertical sufficient height should be there. Adequate surge room for slush of liquid, means liquid is not going to interact the gas again. Mist extractor or eliminator near the gas outlet. So, if the inlet and this engagement section could not separate out some of the small droplet of the liquid, those are going forward or upward in case of the vertical separator or further in case of horizontal separator, these small droplets are just being carried forward with the gas. They need to be separated and they can be separated with the help of a mist eliminator or something put at the end of disengagement section, where the small droplets are going to coalesce, forming amalgamation and creating large size drop, and because of the gravity they are falling down again and getting separated from the gas. So, the job of a separator should be, it is purely mostly gas that is getting out from one point and purely liquid from the other point. Because of the thermodynamics condition, there might be some amount of the gas that is dissolved in the liquid that should be counted. We will discuss that thing later on. Other than these three sections of separator, inlet, disengagement section and mist eliminator, the separator is equipped with some other devices that is for monitoring the performance of a separator, like temperature, pressure, back pressure valve to maintain the pressure, safety relief valve for safety purpose, as well as some other devices like gauge glasses and instrument gas regulator. So, several other devices are also associated with the separator to monitor and operate the separator effectively and safely. If we go further, what we see the design criteria for a separator. If we are having a choice to choose a particular type and size of a separator, what should be the specification of that separator, we should be able to estimate first. Mostly natural gas engineer, they do not design the separator, but they understand the need of the separator. They can go to a particular vendor or supplier and ask for a separator that can meet the need, how much area is available, what is the quantity of the natural gas that is being to be treated, what are the composition of the natural gas those are going to be treated, and of course, what is the cost of the instrument that can be afforded. Considering all these criteria, natural gas engineer can request vendor to provide the catalog. There are several catalog, there are several standard separators available with several internal features other than the inlet condition, disengagement section and mist eliminator. Other internal features like the baffles, plates, safety features, drain area are also the part of separator design. But in terms of a specification, we need to provide a specification to vendor, then only we can choose. We can choose what type and size of the separator may be appropriate for our need, and that could be done the measurement of gas capacity and liquid capacity. As already mentioned, the function of gas separator depends on the fluid stream composition, that is reaching temperature and pressure. So, we know the separator design depend on the fluid composition, the temperature and pressure separator is being operated. So, if we are changing any of them like fluid stream composition or the temperature and pressure, we know the output of the separator will get changed. From the phase diagram we understand changing the composition will change the envelope, changing the temperature and pressure will result different percent of liquid and gas, those can be separated from the same separator. To understand that need, we have to calculate how much gas capacity our separator should have and how much liquid capacity it should have when we are dealing with a particular gas well or fluid well where we are going to install the separator. Sauder-Brown, they had given some empirical correlations. Based on that, we can calculate the gas capacity of oil and gas separator. Actually, they had given for this gas capacity where it says the velocity of the vapor or gas within a separator can be calculated considering the density of liquid phase and density of gas phase. K comes out as an empirical coefficient that depends on several factors, size of the separator and others internal arrangement that is within the separator. We will discuss this in the next slide. Once we know the velocity of the gaseous phase, we can calculate the flow rate by knowing the area or the cross sectional area, that could be pi d square by 4 if it is a cylindrical pipe, and this condition we can transfer to standard condition considering the real gas law that we know PQ by ZRT at one condition is equal to PQ by ZRT at second condition. If we are having one of the condition is like a standard condition, let us say this is standard condition. So, now we know the gas capacity under standard condition we are having when we are having particular gas stream of density rho g for the gas and density rho L, that is getting separated from the separator. So, if we know gas capacity, we can go to vendor will ask what is the liquid capacity you need, because in the function of separator we understand there should be a sufficient surge room for the liquid also, and there is no re-entrainment between the gas and liquid is happening. Thus, it becomes important to know what is the liquid capacity a separator should have, and that can be calculated just knowing the volume of the liquid that is going to be produced when we are feeding stream to a separator. And this numerical coefficient is just arrangement converting from day to minute. This is VL is liquid settling volume. So, for example, here we are having some area where the liquid is getting settled, and this is the area, for example, we want, which is occupied by the gas. So, now if we know the gas capacity and liquid capacity, we can go to vendor and he will tell us different size of the separator in a different types he is having, we can choose one of them. We will see in the next slide, and important is here the temperature and pressure we are operating our separator. If it is change, one of them is change, the calculation will get changed, and again we have to perform the calculation to calculate the gas capacity and liquid capacity to go to vendor. So, I think it is clear from here the parameters gas capacity and liquid capacity becomes important, and when it is a high pressure gas stream, we understand from the literature that it is a gas capacity that dominate the selection, means the volume of the gas that is going to be separated out from a separator or using a separator decide the type and size of the separator should be used. This is the theory behind the empirical expression that mentioned in the last slide, like the Sauder and Brown, they had given this expression. That expression can also be formalized considering the forces acting on a droplet of a bubble. So, the bubble is traveling along with the gas or the vapor velocity is like this, the diameter of droplet is dp, it is going to face or it is going to move considering the forces acting on it. Those forces are drag force and it is balanced by net gravity force, means gravity minus buoyancy forces, and when both the forces are balanced we get the terminal condition, and the separation will happen only and only when the vapor velocity is less than the terminal velocity, and when this situation is happening liquid will come down. We are showing this just to say the empirical correlation given is having some fundamental behind on it, but this is for a very simple case when we consider it is the bubble or droplet or liquid droplet is moving upward in a vertical column, it is considered as spherical, and some other accessories, those are inside the column like the plate and column were not considered. We will see this force balance and its aspects when we are going to design two phase and three phase separator in the next class. We will discuss in little more detail. Now, type of the separator available, you will see there are vertical separator. The vertical separator are mostly used when the intermediate gas oil ratio is there. So, the gas and oil ratio is in the intermediate region, we should choose the vertical separator, and when we are having the high GOR, we should go with the horizontal separator. But ultimately the selection of separator depends on the production stream characteristic, the quantity of the fluid stream is going to be treated, the composition of that fluid stream as well as floor space available. So, for example, the vertical needs very less space. For example, we are having the offshore platform where we need one separator, the best option goes as a vertical separator, and of course, the cost. So, the vertical separator could be for the 2 phase, could be for the 3 phase. As shown for the horizontal separator, this is for 2 phase considering double tube. Double tube means we are having this region where the separation is happening in the upper region and the liquid is just getting down, and we are having some surge volume in a separate tube. That is where the possibility of re-entrainment of the gas and liquid is completely overruled. For the 3 phase separator, we are having 2 separate outlet for both oil and water, considering the 3 phase separation of oil, gas and water system is happening, and you will see several other accessories like safety valve, safety head and other accessories, pressure gauge are also present in this diagram, and they are the integral part of the separator. They are for the safety purpose, they are for the monitoring purpose. And when we are having the spherical separator, the area get reduced and we can install that also in a very compact manner, but it has its own advantage and disadvantage. In fact, all the separators those are available in the market or those can be designed are having certain advantage and disadvantage based on the need, based on the requirement, considering the other specifications or other aspects associated with the separator selection should be considered before making the final decision. If we go in little bit more detail, we will see in a vertical separator, as mentioned, it is for the intermediate gas to oil ratio. It has large surge of liquid, it can handle large surge of the liquid. So, here is the inlet, we are having the inlet and we can create a large surge volume below that for sludge of liquid. From the bottom part we can have a discharge valve for the liquid, and finally, we are getting the liquid outlet from the bottom part, and from the top part we are getting the gas outlet. So, the gas is coming out from the top, liquid from the bottom. There are no chances where gas and liquid are going to contact again, and this is in disengagement section where because of disengagement the small particle or the immediate size of the liquid droplet are getting separated because of the gravity action. But this vertical separator is having the feature of it occupies less area, but the same time fabricating vertical separator is a costly affair. As mentioned already, if you know the liquid capacity or the gas capacity you are going to handle with a particular gas well and you want to install a separator, there are several options. I have just shown some of the size specification of already available or the standard vertical separator. Those are classified on high pressure and low pressure region. If you are having the high pressure region, you know how much liquid capacity you are going to deal, you can choose appropriate size of that separator for the 2 phase as well as for the 3 phase. So, altogether what you are going to get vertical separator for 2 phase as well as 3 phase depend on the volume of the liquid going to be handled. There are different diameter and height separator already designed and available. The internal arrangement like what you are having inside, the obstacle, the baffles, the mist eliminator will be the additional feature, but just considering the height and diameter of the vertical separator we can choose. But this is not as simple as it is appearing, because this is not only the liquid amount, that is considered here, we also have to consider the gas capacity that we are going to face, and considering both gas capacity and liquid capacity, our separator should be designed in such a manner it is not over designed, means it is having more area available than the required, or more volume to be occupied than we are dealing, or it should also not be under designed when it is getting overflowed or it is not able to handle the amount of the fluid being produced. Similar set of the data are available for horizontal separator also. Horizontal separators are having the features, they are widely used for high gas oil ratio well stream. So, when we are having the high amount of the gas oil ratio, we should go with the horizontal separator, and horizontal separator are having this kind of the feature where we are having one end the gas or means the fluid is entering, and immediately when it enters it is going to hit some baffles region, and when the gas or the fluid means gas plus liquid is going to hit the baffles, because of that the liquid will drop down because of the gravity and gas will pass, and when it will reach in this region after the baffles region, you will see the gas and liquid got separated. We are getting the liquid from this part and gas from this part. There are chances where they may get mixed here depend on the temperature and pressure condition. Gas may go to liquid phase, liquid may go to gas phase. That is why this two double barrel separator is designed. The first part is similar to what it is here, how the gas and liquid is getting separated here. The inlet is here, gas and liquid are getting separated here. Gas is going only in this region and we are getting the gas out from here, while the liquid wherever it is getting fall, it is going down to a bottom section of the separator and it can be separated from the bottom part. This three phase is having the similar features where we can get two phases liquid here, and because of their gravity difference oil and water can be separated, and for that purpose we need to install some liquid level devices. Level of a particular liquid is up to this height, and beyond that then it will come out, it should go out. Otherwise both the heavy liquid and light liquid will get mixed. We will discuss these when we will be in the next class discussing the design aspects or some of the procedure of how to design two phase and three phase separator. As mentioned already, this kind of the data are also available for the horizontal separator. Vendor can provide different option in terms of the diameter and length of the horizontal separator. Horizontal separator are having some more features also, like they can be stacked very easily. Once after one we can have a stage separation also. Horizontal double tube separator are low in cost and can handle higher liquid capacity, because here in this double tube separator we can see we are having a separate region where the liquid is being stored. The gas liquid capacity of this double tube separator is high. So, based on the need, based on the features, these can be chosen. For example, if we are just going to deal with the two phase, why we need to go for a three phase separator? We are having three phases, two phase separator is not going to effectively separate the phases. We should go with a three phase separator, and three phase separator is also available in the vertical as well as in a spherical domain also. Spherical separator, like here, this is a spherical separator where the inlet is like this here. It is compact in design and all the things are happening together, like when the fluid is entering inside, it is separating, primary phase separation is happening, then disengagement section is there, mist extractor is also installed in that compact region, and altogether we are going to get the gas outlet from the top and oil outlet from the bottom. These are inexpensive and compact separation arrangement is provided by this spherical separator, but very limited surge space is there, and because of that there is a possibility gas and liquid are re-entering further. Liquid level control in this type of the separator is also very difficult. As mentioned previously, when there is a possibility of two different fluid can go in contact again, we can put some liquid level controller and the liquid level is not going beyond that, accordingly the flow rate is adjusted. So, it is coming out of the separator, but in this kind of the separator where the surge volume or the settling volume of the liquid is very limited, installing those kind of the control level measurement devices will be difficult. Again the same thing, for a high pressure as well as row pressure, the spherical separators are available. Those can be based on just the diameter. Those can be chosen based on the diameter. If we know what is the amount of the liquid we are going to deal with this separator. Again, this amount of the liquid can tell us about the size of the separator, but that need to be verified with the amount of gas that is also going to be handled, or in other terms gas capacity, because altogether both gas capacity and liquid capacity will determine the optimum size of the separator. Already mentioned, it should not be over defined, it should not be under defined. These tables are one type of the guidelines. There are some charts by Sewalls in 1977 and again further in Ikoku in 1984. They have prepared some charts for the separator. They provide more logistic value for the gas capacity. Here with this chart or with these tables, we are supposed to calculate the amount of the liquid we are going to deal, and then calculate how much amount of the gas capacity we need, while these charts provide in terms of the gas capacity. So, considering for example, in the horizontal separator, how much amount of the area or volume available in a separator is going to occupied by the liquid, because the remaining will be for the gas. If we consider the half, 1/3 or 1/4, accordingly we have to choose the size. We have to choose the diameter and length, considering the total volume is occupied by the liquid, and what is that amount of the liquid that we are going to deal. So, with this, what I would like to say, in three-phase separator, as we already discussed for the horizontal, vertical is also having the similar thing, where we are having two different zone to take out the two liquids separately. For example, the light liquid from here, heavy liquid from here, as we were having in case of the horizontal separator, where the oil was coming here and the water out was installed here. Other than this, the three-phase separator can be accomplished in any type of the things. As mentioned, they can be horizontal, they can be vertical, they can be spherical, or they can be in any design. The features about the three-phase separator is, it is very difficult to install in a spherical mode because of their limited available internal space. So, if we are talking about three-phase separator in a spherical geometry, we are having the difficulty. Otherwise, oil, gas and water separator are commonly available for two-phase as well as three-phase. So, there should not be any difficulty when we are dealing with the three-phase system. In fact, three-phase system are important when we are performing some specific kind of the test with the well, when we are sure there will be a three-phase present, like the water will also get produced along with the gas and oil. In that case, we should go with three-phase separator only. We will discuss this thing a little bit more detail in the next lecture, but let us focus on the factor those affect the separation. Already discussed operating temperature, operating pressure as well as the composition. So, for example, a particular well is producing the fluid or the gas with certain composition, those are not going to change that much, but the temperature and pressure, that is in the hand of the operator. He can change to collect more liquid, or he can operate at a higher pressure where the separation is happening and the gas is also carrying some of the higher hydrocarbon. Ultimately, it is in the hand of operator to separate these phases with the help of setting the pressure and temperature of this separator. But how to choose that, how to decide that thing? In general, operating pressure is increased, we are going to get more liquid recovered. If you remember from our phase diagram, we know when the gas is entered in a two-phase envelope and at a higher pressure, the tie line says we are at a higher percent of liquid. Similarly, operating temperature, if we reduce the temperature, the higher hydrocarbon will phase out from the gas phase and reach in the liquid phase, and that is where in both the cases, when we are increasing the pressure and reducing the temperature, liquid recovered at the separator will go on. Question comes how to choose those temperature and pressure condition, because in previous calculation when we were dealing about these gas capacity and liquid capacity, those are empirical formula given by Schroeder and Brown, and those empirical formula need K and that is not known. Is there any procedure through which we can understand the amount of the liquid and the amount of the gas those are going to be treated with the hull of a particular separator, and if yes, how to perform that calculation? And for that there is a procedure called flash vaporization calculation, and that procedure will allow us to perform certain calculation and find out optimum pressure and temperature to achieve maximum liquid recovery. If we perform that calculation at different temperature and pressure condition, we can see how much liquid is going to be recovered. Or other way, the flash vaporization calculation is going to give us the strength how to perform calculation at a particular temperature and particular pressure for a particular fluid stream to know how much liquid and how much gas volume is going to be treated by a particular separator, and that is what we need if we want to go to a vendor to ask what size of the separator I should use. He needs the capacity of liquid and the capacity of gas, those are going to be handled by a particular separator. Sometimes it is not practical to operate at optimum condition, we already mentioned, like storage system vapor losses may becomes too great and we are losing the vapor. That is why it is not important to run under the optimum condition, but at least flash vaporization calculation will provide us the guidelines how to calculate the amount of the liquid and gas that is going to be produced when a stream of fixed composition is entering to a separator. Let us understand how this flash vaporization calculation can be performed and on what principle it does work. In flash calculation, first thing is assume phase equilibrium are reached in the separator. So, the gases of some composition, the gases those are producing from a particular well are entering in this separator. This is my separator, this is inlet, this is let us say gas out and this is liquid out. So, we know at the inlet condition the fluid is entering into the separator, we can measure the composition by performing the gas chromatography. Assuming we know the composition here, the fluid is entered in the separator that is set at temperature T and pressure P. Another assumption we are going to make, the phase equilibrium is achieved for each component present in the inlet stream, and at that condition what is going to be the product from separation can be predicted. How they can be predicted? With the help of the concept of equilibrium ratio, that says K I is equal to Y I by X I. K I is liquid vapor equilibrium ratio for a particular component I, while Y I represent that component's mole fraction in the vapor phase and X I represent the mole fraction of that particular component in the liquid phase. So, if we know K I of a component, we know how many moles of that component are in the vapor phase and how many moles are in the liquid phase. That K I will depend on temperature and pressure condition, because the partition happening in a liquid phase and vapor phase will depend on the temperature and pressure condition, as well as the mixture presents what are the composition of that mixture. So, let us say K I is defined as Y I by X I. I want to know K I. How to know K I? That is another question that can be estimated with the help of equation of states for a hydrocarbon mixture. Those are developed by Ahmad in 1989. Another way is presented by Standing in 1979, and that method says you can predict K I equilibrium ratio value for a particular component I using this expression, and that expression is having pressure in the denominator and some coefficient A, C, Fi. A and C are the function of pressure again. In the quadratic form, we can calculate A and C if we know at what pressure that particular component is exposed. Fi is related to temperature and boiling temperature of that component, because we are going to calculate Ki for a specific component that is present. So, this is a situation like we are having the stream which is having n component, and that stream is just exposed to a separator and suddenly exposed to a particular temperature and pressure. How the separation is going to be, how many moles are going to vapor phase, how many moles are going to liquid phase, and for that the component properties are also important, and the Fi related boiling point of that component, while Bi that is appearing on Fi is relating the critical pressure and boiling point of that component in the system as well as critical temperature. So, the component, individual component, we know it is very not difficult to find out the critical properties or the boiling point of that particular component. Several references books are there. So, the feed that is entering to a separator, if we know the composition, we can go to literature, we can find out its properties. Those are required to estimate the value of Ki. The properties are boiling point, critical pressure, critical temperature, and if we know, using this empirical formula we can calculate the value of Ki, equilibrium ratio. Once we know the equilibrium ratio for a particular component I, we can calculate the ratio of Yi by Xi. Still we do not know how many moles are in the vapor phase, how many moles are in the liquid phase, but we know the ratio of moles in vapor phase to mole in liquid phase, and that is going to help us if we can set up the material balance across this separator. So, these are the Zi is the feed is having mole of that mole fraction of that component Zi, and that is going to be exposed to temperature T and P. We are having total component N, those are entering here. Considering 1 mole of feed is entering, it means we can classify how many moles of that total 1 feed mole is going to be in a vapor phase and how many are going to be in a liquid phase, and if we sum both of them, that will be equal to the mole fed into separator. In that case, NL plus NB will become 1, and that is at the operating condition, means within the separator, and those value of NB and NL will depend on temperature and pressure. For compound I, we can write number of moles in liquid phase multiply by the mole fraction of that component Xi will give us the total mole of that component in the liquid phase. Similar can be done for the vapor phase, and summation of that component in the liquid phase and vapor phase will be equal to the moles of that component getting into separator. We can replace either Xi or Yi using the equilibrium ratio Ki is equal to Yi by Xi. If we do so, we are going to get this relationship. From here we could eliminate Yi, we just got the relationship in the form of Xi, and now Ki appears here. If we rearrange this, we are going to get in the form of Xi, how Xi, the mole fraction of component I in liquid phase at the temperature pressure conditions, going to be Zi by NL plus Ki NB is going to give us that value of Xi. We know summation of mole fraction for all the component from 1 to Nc, Nc is total number of component Nc. We can say summation of Xi is going to 1. We can do the summation on both left hand side and right hand side, we are going to get this expression. Similar we can do for the vapor phase. We can replace this Xi by Yi by Ki using the equilibrium ratio, adjusting it in the form of moles of component I in vapor phase. summing it for all the component, we are going to get this expression. So, now we got the expression for x I, summation of x I and summation of y I in form of z I, means the feed composition, and k I, the equilibrium ratio that depends on operating condition. If we subtract both, we are going to get this equation, very simple equation, and if we rearrange that equation, we are going to get. Now, what we did here, we were having NL and NV, total moles in the liquid phase and total moles in the vapor phase. Now, by doing the rearrangement, what we could do, because we know NL plus NV is equal to 1 of them we can replace, and we got in the form of NV, means number of moles in the vapor phase, total number of moles in the vapor phase. Now, we can set up mathematical equation, because we know Z I, K I for individual component, whatever the feed is entering, knowing the temperature and pressure, we know K I for individual component, and if we can find out the value of NV, total number of moles in the vapor phase, that is going to satisfy this condition, we are in a well good condition to calculate the other parameter associated, and that can be done by using some iteration method that we discussed in our first week lectures. We can optimize this with the help of Gold-Seek or Newton-Raphson method, and can find out the value of NB that is going to satisfy this condition. And once we know the moles in the vapor phase, we know the moles in liquid phase also, because NV plus NL is equal to 1. If the value of K I are known, we can calculate the NV and NL, and once they are known to us, we can calculate X I and Y I. Once we know X I and Y I for individual component, what we can calculate? The apparent molecular weight of the liquid phase, apparent molecular weight of the vapor phase, by using the summation or the chain rule or the mixing rule. Once we know the apparent molecular weight of the vapor phase, we know how to calculate the specific gravity, that is using this expression we can calculate that thing. For the liquid phase, we are provided one expression by standing, and that says you have to account the oil or the liquid that is separated out, what is the specific gravity of that, what is the specific gravity of the solution gas, some of the compound remains in the liquid phase, what is the specific gravity of those compound, as well as gas solubility of the oil, means how much gas is still present in the oil phase or in the liquid phase. If these parameters are known, we can calculate the rho L. So, by performing the flash calculation, we can calculate the density of vapor phase as well as density of liquid phase, and once we know these things, we can calculate the volume of vapor phase under standard condition. We use this PV by ZRT at one condition to PV by ZRT at two condition. We can convert that into standard condition. Some coefficient may appear here. Important is NV. NV is required. Now, with the help of flash calculation, we understand how to calculate NV. Similarly, one more parameter is appearing here, that is CHAD, compressibility factor. From our natural gas properties class, we understand how to calculate the compressibility factor for a given composition at a particular temperature and pressure, and Brill and Bax method can be used to calculate or estimate the value of compressibility factor. If we know the volume of the gas or the vapor that is going to be treated by a separator, and similarly we can get for the liquid also. Once we know the total number of moles, multiply by the molecular weight will give us the mass. Mass divided by the density of that liquid phase will tell us the volume of liquid phase. Once we know the volume of the liquid phase, volume of the gas phase that is going to be released out from a separator, we know we can calculate the gas oil ratio, and that gas oil ratio is very important parameter, because that says what type of the well it is. It is gas well, it is condensate well, or it is oil well. I think now the procedure is clear how to set up the flash calculation. We are going to understand this with the help of one example. So, in that example, what is given a feed of this composition is entering into a separator, and the compositions with the help of chromatography or other devices we could estimate what are the composition of that feed, and that is come out as it is mostly dominated by methane with some other compound present. It is also having some inorganic gases. So, the separator is set at pressure 600 psi and temperature 630 Rankine. This is temperature, this is pressure. The feed of this composition is entering to a separator. We know the composition Zi. What next we are supposed to do, knowing the composition of non-compounds, we can go to literature, use the properties of those compound like critical pressure, critical temperature, we can calculate the factor, those are appearing in our equilibrium ratio calculation Ki. This is my equilibrium ratio. So, for each component I can get the value of Ki. Now, if we go further, we could calculate the Ki value, we know the Zi value. If you remember the expression that allow us to choose particular value of Nb that can satisfy that expression, we can set up in the Excel or in a mathematical program, and that simply says summation of individual compounds expression of this like Zi multiplied by 1 minus Ki divided by Nv, total number moles in the vapor phase, Ki minus 1 plus 1, altogether this expression if calculated for individual compounds and perform the summation, and when the summation is 0 for a particular value of Nv, that is the solution for Nb, and we know how to do that. We can set this cell by changing this cell Nv to set this cell should reach value 0 with the help of goal seek. So, what we can do? We can put summation of this, that is here we want this cell to be 0 while changing this cell Nv, and when we perform this goal seek we got the answer, the Nv value is 0.9443. So, most of the compounds those are present in the feed are going to be in the gaseous phase, and that should be because the composition of the feed are mostly dominated by methane, and the temperature and pressure condition are also favoring, like the other lighter compounds are going more towards the vapor phase, and 1 minus Nv will give us the value of Nl. Once we know Nv and Nl, knowing the Zi, we can calculate Xi and Yi. We got Xi value and Yi value. We know the molecular weight of each compound present in the feed. They are going to be either in the gas phase or in the vapor phase. We can calculate apparent molecular weight of the liquid mixture, apparent molecular weight of the vapor mixture. Knowing apparent molecular weight of liquid phase and vapor phase, we can calculate density of the vapor phase as well as volume of the vapor phase. Using the equations shown in the previous slide, we can calculate the density and volume for both the phases, liquid and vapor, and if we do so, we are able to calculate GOR, gas to oil ratio. So, the flash calculation will tell us how we can calculate GOR along with other things. So, in summary, flash calculation is based on equilibrium, that says Ki equilibrium ratio is a ratio of Yi by Xi. Standing had given us a set of the expression that allow us to calculate the value of Ki at a particular temperature and pressure, and once we calculate this Ki, we can use this expression performing the iteration towards NB to get the value of NB. Once we know NB, we can know NL. Knowing NL, NB, Zi, Ki for a particular composition, we can get the mole fraction in the liquid phase. Similar we can get for the vapor phase. Knowing all this, we can get the density of liquid phase and density of vapor phase. Important point is here, it depends on the compositions. If Zi compositions are changed, entire calculation will get changed, because it depends on Zi. If temperature or pressure is changed, because the calculation of Ki depends on temperature and pressure as well as composition. With this, I would like to end the lecture on separation of natural gas first. In the second lecture on the same topic, separation of natural gas, we will further increase our knowledge or discussion on separation side, like stage separation procedure and the scheme of low temperature separation. Further, we will discuss some of the aspects of or the procedure of designing 2-phase and 3-phase separator, both for horizontal and for vertical separator. Thank you very much.